Hi, I'm Professor David Farina. In today's video, we're going to be talking all about telescopes and specifically about space-based telescopes. Why would we spend all of the money to put a telescope into space? Why wouldn't you just put it on the ground? That's a great question. Let's get into it. One of the most important telescopes, and by far the most famous telescope ever, is the Hubble Space Telescope. The Hubble Space Telescope is an amazing instrument. It has been collecting data since before I can remember, over 30 years. And the Hubble Space Telescope is iconic because it has produced some of the most fascinating and inspirational images of space. But why? How is it possible? What makes the Hubble so amazing? Well, it has to do with the fact that the Hubble Space Telescope is not dealing with the atmosphere of Earth. It's in outer space, where there's no atmospheric seeing, there's no distortion, we don't deal with day and night, we don't deal with any kind of clouds and weather, any moisture in the atmosphere. The Hubble Space Telescope is dealing with a near vacuum of outer space, and as a result, the Hubble can take crystal clear images at any given time, 24 hours a day, 7 days a week. That's pretty good. There's no other place on Earth where this is possible. And so the Hubble has a distinct advantage. The high-resolution images of the Hubble Space Telescope is what makes it so iconic. These images of a galaxy can be zoomed in upon in an unimaginably detailed way with the Hubble Space Telescope. Also, other observatories are found in outer space because the type of light that they're working in, like parts of the infrared radiation, are not possible to see from the ground. We need to go up to very high altitudes or space in order to kind of get around this atmospheric absorption. And so infrared observatories in space have, once again, a very distinct advantage because they're not dealing with Earth's atmosphere. We do, however, have balloons and also the SOFIA spacecraft, the SOFIA airplane, which is a 747 jet that flies at very high altitudes in order to produce infrared images. Now, infrared cameras, they use liquid nitrogen in order to cool the camera so that we bring down the temperature of the camera, making it more sensitive. Think about it. What is infrared? Infrared is simply heat. So if we had a warm camera system, then the heat of the camera itself would be producing a significant amount of noise. So by cooling the camera with liquid nitrogen, we are eliminating a large amount of that extra noise, and as a result, making a much more sensitive camera. So here's one of our examples of a weather balloon that's capable of taking an infrared telescope up into outer space, or close to the edge of space. Another good reason to go into outer space is for UV astronomy, ultraviolet. Ultraviolet, fortunately, doesn't make its way through the atmosphere very easily. Now, some of it, like UVA and UVB, that's the same type that you use skin products like sunscreen to protect yourself against these harmful rays. If it weren't for the Earth's atmosphere, the UV radiation from space would actually, and from the sun in particular, would cause significant amount of cancer, and it would likely wipe life right off the Earth. So without the atmosphere blocking UV, life on Earth probably would not exist. So you must go into space to see in the UV spectrum. Now, when we look at the sun in various different types of radiation, we can see different things. Like I said earlier, similar to a doctor using an X-ray or an MRI, we look at different types of light to see different things. And so in this first image, you can see a bunch of detail on the surface of the sun. We can see this prominence sticking out. We see all the different little spots here, which are called granulation. We can see a sunspot. Here on this image, we can start to see a different set of details. This is the exact same timing, so here's that same sunspot. Notice you can start seeing some of the magnetic field lines sticking out here, some of these filaments. You can see all of this magnetic carpet. This is basically, it looks like a shag carpet coming out. Here you can see it even in greater detail coming out in this green image. And just based on the type of light that we're looking at, we see different things while looking at the exact same object at the exact same time. So the several satellites are up in outer space looking in the UV parts of the spectrum right now, and here they are. These images that you're seeing of the sun are from the STEREO spacecraft, which is looking at the sun in stereo. It's actually two spacecraft looking at it from different angles, and so as a result of these two separate angles, we can get a 360-degree image of the sun at all times, 24 hours a day, 7 days a week. And this is really important because our sun is violent, and we want to make sure we're protecting ourselves against coronal mass ejections and solar flares. These things could wipe out our power grid, and if we know in advance, we can prepare for them. So it is an important initiative that we monitor the sun at all times. Please keep in mind that as we go up higher and higher to these superior to visible light frequencies, we've got short wavelengths, high frequencies, and they also are going to be produced by the hotter objects. So as we go past the visible spectrum, things are going to be getting hotter and hotter in terms of the objects that we're observing. Next up is the X-ray style of telescope. Now, of course, an X-ray can penetrate right through your skin to see your bones, but that also means that it can penetrate right through a normal mirror. So X-ray telescopes use this glancing style mirror, where the light goes through these nested cylindrical mirrors, and the light simply bounces on a very low angle until finally we can approach a focal point. So this way we can focus the light, but there are some drawbacks to this. It means that we lose some resolution in this process. We can detect things with lower detail. So the Chandra X-ray Observatory is one of the most important observatories of all time, and it is observing in the X-ray portion of the spectrum and capable of seeing things that are of very high temperatures, tens of millions of degrees in temperature, things like supernovas, things like black holes, the hot gas and dust that's forming around energetic magnetic field lines like around Jupiter and Saturn. So all of these X-ray producers are a lot of times observed through the Chandra X-ray telescope. Here's just another picture of its mirrors. This is the actual Chandra mirror, which it says here is each mirror is 0.8 meters long and between 0.6 and 1.2 meters in diameter up front. Not big, but very important because it's in outer space. So this is an X-ray image of a supernova remnant of Cassiopeia A, which is one of the most important and iconic of supernova remnants. Now finally, gamma ray telescopes are also available, and through gamma rays we're seeing the most highly energetic particles of all of the electromagnetic spectrum, and they have the ability to show us once again things that are extremely hot, and the most important of these observatories is by far Fermi. Now, looking at the electromagnetic spectrum in different wavelengths of light, this is the Milky Way all-sky images, so we can see how the Milky Way looks in the radio spectrum. There it is. This is how it looks like in the infrared part of the spectrum. Of course, this is what the Milky Way looks like in visible light. Here's what it looks like in X-rays. And here's what it looks like in gamma rays. Notice, please, that the book indicates along each of these little spots what type of light we're looking at. So radio, infrared, visible, X-ray, and gamma ray. And they do a very good job in this book on how to label each image that they show. So once again, here's a picture of the multi-wavelength Milky Way. A very good NASA website, by the way, multi-wavelength Milky Way. Just type it in a Google search. So thanks for watching our lecture today on telescopes, specifically on space-based telescopes. I hope you learned something interesting. And if you did and you'd like to learn more, please subscribe and click like on this video. And if you'd like to find out next time I make a video, click that little bell at the bottom so that you get a notification each time. Thanks a lot and have a stellar rest of your day.